All right, so can you see my screen sharing well?
Yep.
Okay, thanks. So yeah, Bill forgot to say something. He asked me earlier whether to mention to everyone that I'm partially bald, and this is actually true. But I guess those of you who know me, then you know this. But anyway, thanks for the intro, and thanks for SolidQ Flex Services for arranging this session, this webinar. So we'll talk about one of my favorite subjects, which is T-SQL. I'm sure a big surprise for many of you. So just a note before we start with the technical part, I uploaded the source code for the session into the website tsql.solidq.com. So let me go quickly there and show you how you get there. Just note, it starts not with www, but tsql.solidq.com. And then within it, if you press the link for resources, one of the first links, the last one in this kind of bullet list, is source code for recent conferences. And when you go there, the bottom link that you will find contains the entire source code for this session. So feel free to download it and play with the code samples later on. All right, so the topic of the session is a couple of the most fundamental access methods that the SQL Server Optimizer uses, seeks and scans. So first of all, we'll talk about which is better. It's kind of a classic question. Is it better to have a seek? Is it better to have a scan? We'll then take a look at cases where we have a given task, we come up with a solution, and talk about this examples where the optimizer does a pretty good job picking up a fairly optimal plan without us needing to do any kind of special tricks. But there are cases where the optimizer doesn't just have enough logic within it. It doesn't have all of the possible ways to solve a given query. So even though theoretically there are more optimal plans, the optimizer just doesn't know how to choose them. So we will look at how we kind of nudge the optimizer in the right direction, mainly by applying query revisions. And I'll make a point in this session to try and avoid, those techniques that force the optimizer to do things with specific hints and so on. I'll try to use pure kind of SQL-based solutions that just get optimized better, right? So let's start with the question, what is better, a scan or a seek? And of course, the answer is, it depends. Well, one of the answers that people don't really like very much to hear, but the reality is this, that it's not like always a scan is a bad thing and a seek is a good thing. It's really a matter of what we are trying to achieve, what are the data characteristics, and what are the indexes that we have available, whether one is better than the other. So my focus in this session will be all kinds of querying tasks that involve calculating something per group. Take an example, computing a maximum order ID per shipper or a maximum order ID per customer. So which strategy with an index that is created on the group element and any additional elements that are relevant there depends mainly, in such cases, on the density of the group element, right? So for example, if we want to compute the maximum order ID in our orders table per shipper, here most likely we're looking at very kind of dense data. So look at the left side of the screen. You can see an index that we define on the shipper ID and the order ID within it. And then imagine we have a very small number of shippers. So you see there's a very small number of kind of groups within the index leaf. And the most efficient way to go after that maximum ID per shipper will naturally then be to apply a seek per shipper. So the kind of pattern here is when we have very high density, we want to see seeks happening in the index. But then again, if we had a similar request that said, give me the maximum order ID per, say, customer, and we had lots and lots and lots and lots of customers, each of them having an average, let's say, a very small number of orders. So that's the right side of the slide. Here, you realize that if we go and apply a seek per customer, we'll just end up with many seeks, and the total cost here will be far greater than just doing one pass over the leaf of the index and kind of grabbing the maximum ID per customer in this case. So here, the pattern that has low density of the group element typically will benefit from applying a scan within the index, right? So let's start examining more kind of specific, examples. So let's start with a case where we have very high density. Like what I mentioned, I want to compute the maximum order ID per shipper. What's the optimal index that we can create here? We'll create an index that starts the key list with a shipper ID. Remember, that's our group column. So you can see we have a consecutive section within the index per shipper. Shipper 1, shipper 2, shipper 3, and so on, right? And then the second element in the index key list will be order ID descending. So the very first row within each shipper section will actually be the one that contains the element that we need to return. So imagine that our orders table has, say, 10 million rows, and the company works with 10 different shippers. So with 10 million rows, very likely you will be looking at an index that has 4 levels within it, meaning that the cost of a seek that will get you to the leaf of the index will be 4 random reads. And then in the leaf level, with the data that we have there, the rows are pretty short, we are looking at about 36,000 pages, right? So you realize that the cost of a full scan within the leaf of the index will simply be 36,000 page reads. So remember, the cost of one seek is 4 random reads. The cost of a scan is going to be 36,000 sequential reads, okay? So with the shipper ID as our group element and so few shippers involved, if we want to get the maximum order ID per shipper, we are going to be better off with a strategy that will apply a seek per shipper. So think about it. With 10 seeks, we're going to get only 40 random reads. With a scan, 36,000 reads, it's quite clear that the seeks strategy is a better strategy here. And then let's take an example with very low density. So I mentioned kind of an alternative group element, the customer ID. I need the maximum order ID per customer. And currently my table has 2 million customers, each you can see with an average of just a few orders, right? Remember, we have in total 10 million orders. So think about it. If we write a solution that collects the maximum order ID per customer with a seek per customer, we're going to end up with 2 million seeks. Think about it. It's going to involve 8 million random reads, which is obviously much less efficient than a strategy that will go ahead and do a scan, and as we scan the data, collect the maximum ID per customer. All right, so now that we know which strategy is better, and remember, the maximum order ID per customer is just a basic example. There are so many examples where we need to perform some kind of activity per group. And the maximum or a group element with an aggregate is just one of many examples. We will go over 3 specific examples, and I'll actually start with one that involves a solution that the optimizer does a pretty good job in optimizing it without intervention. So when the optimizer does a good job actually analyzing or exploring alternative plans that when we have high density, we'll naturally use seeks, and when we have low density, we'll naturally use a scan, we just need to let it do its thing. You know, as developers and IT people like to say, when it works, don't touch it. And I've even heard a joke talking about, a father and a son walking out there, and the son asks the father, why does the sun rise in the east and set in the west? And the father says, it works, simply don't touch it. So that's what we're going to do. In those cases where the optimizer does a good job, we want to let it do its thing. It's in our favor, obviously. Just because when the data characteristics change, the optimizer will naturally change its choice. So one of those classic examples is what's called semi and anti-semi joins. So I'm guessing most of you are very well aware of what semi and anti-semi joins are, but just for the sake of the example, make sure we're all on the same page. A semi-join is when we're looking for rows in one table provided that the related row exists in another. We need to return the elements only from one of the tables, hence the semi part of the semi-join. So a semi-join means show me rows in one table if they have a match in another, like show me shippers if they have related orders, versus an anti-semi-join that will say show me shippers only if we cannot find any related orders. So when we use the exist predicate or the not exist predicate to fulfill a semi or anti-semi-join, the optimizer uses mainly join algorithms and does a pretty good job between the seeks and scans strategy. So let's see examples with both shippers and customers. We already know the kind of data characteristics with a small number of shippers, a large number of customers. So let's go after shippers that have related orders. Very basic, select from shippers. Let's name it in short S, where exists, and now related orders. So select from orders, let's name it O in short, where the O shipper ID is equal to the shipper ID. So most basic kind of implementation of a semi-join with very high density. So let's take a look at the query plan. Let's make sure that we have performance statistics enabled. So set statistics, IO, and time on. Right, and then let's go ahead, run our solution. You see kind of super fast solution. Look carefully at the query plan. Pretty basic plan after all. You see the shippers table scanned. Notice we're getting 10 shippers back, and then a loop is going to execute 10 times. Each iteration, notice, will do a seek in an index that we prepared on shipper ID and then order ID as the second key. We have a couple of additional elements that are included that I will use in some later examples, right? But what's critical for our example is the fact that the index contains shipper ID as the leading key and order ID, descending actually, as the second key. So beautiful plan, the perfect one for high density. You see very small number of reads, and then in total, you know, almost nothing in terms of the runtime. It's only 7 milliseconds it took to run. Just to give you a sense, if we force it with a hint to use a scan strategy, to do this, I'll need to tell it to use a merge join. We have covering indexes on both shippers and orders. So if I go ahead and force it to use a merge join algorithm, it will go with a scan strategy. So let's say merge join. Then let's go ahead and run the code. It will take much longer to complete. So look at this. It took it, notice, you know, 2 seconds. It was just 7 milliseconds before, and now it takes it 2 seconds. And notice the net CPU time. It's almost 6 seconds of net CPU time. And you can clearly see why. It ended up doing a full scan of the index in the orders table, and that's the 10 million rows that I mentioned earlier. So take a look at the query plan. You can see shipper side is tiny. This is kind of negligible, but the critical thing for us here is the full scan that we get in the orders table, and then the merge join that basically merges the information. So you see, when we didn't intervene, when we didn't incorporate this hint, we just let the optimizer do its thing, it picked the right plan. Now try a similar thing, but this time looking for customers who placed orders. Let's go and change here from shippers to customers. And then let's just name it in short C. And then where exists orders, where the order customer ID is equal to the customer ID. So same kind of query pattern. I won't run it because we have 2 million customers in the data. So just to show you the query plan that we get, I'll look at an estimated plan. Observe, it is a merge join without us needing to instruct it. You see a scan of the customers table. Observe, we're getting 2 million rows back, a scan of the orders table, and then a merge join that takes place between them. So now comparing them side by side, you can see when we had low density, we ended up getting the scan. When we had high density per shipper, we ended up getting a seek. Same will happen if we apply an anti-semi join. Namely, let's go ahead and tell it not exist. So show me shippers only if they don't have related orders. And in a similar way, show me customers only if they don't have related orders. And you will see also here, also for anti-semi joins, the optimizer is certainly capable of using different strategies here. We have a loop strategy, a merge strategy that will rely on scans, and we even have a hash strategy if we don't have a proper index in place. But anyway, notice with shippers, again, we get per shipper a SIC. With the customers, we get a scan, right? So that's an example where it works and we don't want to touch it, right? Now, let's talk about examples where the optimizer just doesn't do a good job, right? The way I like to think about it is, imagine that we have some kind of a pond, right? In the semi-join option, we have all kinds of ways to get to the other side, including a bridge, you know. So we do have a walkway that allows us to take the longer route, you know, but we also have the bridge that allows us to take the shorter route to our destination. With the semi-join, we have both options, and the optimizer figures what's faster. With the bridge, we walk. With the, you know, maybe the driveway, we can take a car. So depending on our options, we will choose the right, you know, means to get there. But with examples like applying a simple group by and a max or a min aggregate, or fulfilling what's called a top n per group task, we are basically missing the bridge in a way. Yeah, so we have the pond. We only have the kind of one way to get to the other side. And what we're about to do is kind of build that bridge in a way, right? By writing the query in a completely different way to what maybe is the intuitive one for us, okay? So let's take the example with the grouped min or max. So what is the most intuitive way to write a group query that returns the minimum or the maximum? Well, obviously, we'll say group by the shipper or the customer, basic aggregate, max order ID or min order ID to get the result. Now, let's see what the optimizer does. So let's take an example where actually a scan is a good thing for us, which is what the optimizer will do by default. So remember, low density, we want to see a scan. So if we say select from orders, and then simply group by the customer ID, and then per customer, go ahead and give me the maximum order ID. There's only one strategy that the optimizer knows to use in terms of 6 versus scan, I should say, because within the context of an aggregate, the available aggregate algorithms include both an order-based algorithm called stream aggregate that needs the data to stream to the aggregate operator in group order, and then there's an alternative hash-based aggregate algorithm that doesn't need the data to be processed in group order. So between the two, the optimizer does have logic to know, based on cost estimates, when to use the order-based algorithm and when to use the hash-based algorithm. But both of them are based on scanning the whole thing. So notice, in our case, since we have the right index in place, remember, I told you we have an index on customer ID with order ID descending as the second element in the key list. It's a very kind of straightforward choice for the optimizer because the data is already sorted by the group column. So it just does an ordered scan of the index in question. You can see the ordered property is true, and then it can happily go ahead and do the stream aggregate. If the data was not already ordered in an index, then the optimizer would need to choose between adding an explicit sort operation to the plan after scanning the data in no particular order and then support a stream aggregate versus using a hash table to arrange the groups within hash buckets. Typically, when we have a small number of rows, the strategy that sorts and then performs a stream aggregate is more efficient. When we have a larger number of rows, there's some kind of a tipping point where the hash aggregate becomes more efficient. But I'm digressing a bit. That's kind of a side note. The critical thing for our discussion, the optimizer only has a scan strategy to handle a group query. In this example, we're pretty happy with it because we have very low density. But imagine we had very high density. So let's do the same thing, but with shipper ID. and then say, give me the maximum order ID per shipper. Let's go ahead and take a look at the query plan. First of all, look how long it takes it to complete. Remember, all we have is just 10 shippers. 5 of them actually shipped orders. So you can see within the orders table, we end up with only 5 groups. But it took 2 seconds for the query to complete. Why? You can see why. We ended up with a full scan. It is an ordered scan that then supports a stream aggregate. And in fact, because we have a large number of rows per group, the optimizer even decided to perform what's called the local global aggregate. Namely, it splits the rows in the group to multiple threads, and then each thread operates locally on the rows in that thread. And then we have a global aggregate that aggregates the results of the local aggregate. So we also have nice kind of consideration for parallelism treatment and so on, but still it is an extremely inefficient plan for this kind of data scenario. What we want to see is not a scan of 10 million rows that costs us, remember, about 36,000 reads, and then takes over 2 seconds to complete with close to 8 seconds of net CPU time. What we want to see is a scan of the shippers table, and then we want to see a seek per shipper. Now, it's a bit of a stretch to expect the optimizer to go and figure out, hey, I have a shippers table, let's go to the shippers table and per shipper do some activity against, you know, our index on orders. But think about theoretically what they could have added into the optimizer to make it more efficient. So if we think for a moment about the index, right? This is our index. And then imagine we have within the index currently only 5 shipper groups, right? Only 5 shipper groups. So think about a theoretical plan that currently just doesn't exist in the optimizer, where the optimizer just starts a scan here just to collect the minimum shipper ID. And then here for the minimum shipper ID, it can already collect the maximum order ID, because remember, our index has order ID descending within it. So the very first row is already the maximum order ID for the first shipper. But now having the shipper in our hand, we can go and perform a seek looking for the first row where the shipper ID is greater than the previous shipper ID, and then scan 1 row ahead. And here is the maximum order ID for the second shipper. And same way now go and do a seek looking for the first row where the shipper ID is greater than the previous one, and so on. So you realize it's certainly, theoretically at least, achievable with only 5 seeks basically here. So think about the potential. But like I said, there are some things that are not part of the optimizer currently, even though they could have been theoretically. And we need to now kind of build that bridge that I was talking about. So how do we get a seek per shipper and also eliminate those shippers that don't exist in the orders table? The easiest way, I think, is to use the cross-apply operator. So let's go ahead and do this. So we will say select from shippers. Let's call it S in short. And I'll try not to get into too much detail because I want to leave like 5 to 10 minutes for questions, hopefully. So I want to make sure I don't go too much into detail here. But anyway, I'll go and say query the shippers table and then cross apply. And now the query that we will apply against the orders table will say, give me the top 1 order ID from orders as O, where, of course, the O shipper ID is equal to S shipper ID, and then order by order ID descending. And then in the outer part, we'll go ahead and return the shipper ID from S, and of course the order ID from O. So let's see the query plan. First of all, let's run it, see how long it takes. Just to remind you, the group by solution took over 2 seconds to run. It applied 36,000 reads. It required almost 8 seconds of net CPU time. Let's run the apply solution. Look at this. I didn't even lift the finger and it already finished running. So it took almost no time because it performed exactly the strategy that we were aiming at. And that's how apply gets optimized when you have a proper index in place, right? And we do, right? So you can see how we scan the shipper stable. That's very negligible amount of work. We do get 10 shippers back. 5 of them handled orders. So for 5 of the 10 cases, we will get a non-null match. All those empty sets are going to cause the left row to be excluded. It's a bit similar to an inner join here. For those of you who are familiar with apply, when the left row doesn't get even a single match back from the right side, the left row isn't returned, and that's the desirable effect in our case. Therefore, we use cross apply and not outer apply. But anyway, you can see how we do a seek to the beginning of the current shipper section. You can see in the seek predicate that we're looking for the row where the shipper ID is equal to the one from S shipper ID. And you can see also, if we look closely at the properties of that activity, that once we reach the leaf, the first row for the current shipper, the scan direction is forward. Why? Because in the index, we defined the order ID in descending direction. If we created our index with order ID in ascending direction, it would simply go to the edge of the shipper section and then start scanning backwards, but it will be almost an identical plan. Now look at the performance statistics, right? Look at this. It's like we anticipated close to 40 reads, because for each of the 10 seeks, we pay something like 4 reads. The activity against the shipper is, of course, negligible. And then look at the runtime. It's just 3 milliseconds of runtime, and it's not even measurable how much CPU time it involved. And then if we go ahead and compare the two strategies side by side, look at the difference between the performance scores. It's just amazing to see how the optimizer evaluates that the cost of the first one is so high compared to the second that it shows as 100% versus 0% for the second, right? So like I said, there are things that the optimizer just doesn't know how to do for certain types of queries. For the classic group query, it simply doesn't have the seek strategy. So you want to keep in mind, what are the data characteristics? Do we have a low density? Stick to the group by. You have high density? Well, replace it with the cross apply alternative. Obviously, if we use the cross apply alternative, when we have very low density, we're in big trouble. I mean, think about it. Here, this would mean 2 million seeks that will take place. So you want to make sure that you use each of the solutions in the right circumstances. I'm afraid it's not like the semi and the anti-semi joins where the optimizer will know to do the right thing. Okay. All right, good. Now let's proceed to the third scenario. Quite similar in the sense that also here we're going to get only one strategy depending on the kind of query that we write. So the kind of task that we have is the classic so-called top n per group task. Top n per group means we want to return a certain number of top rows for each group based on some order. For example, show me the most recent order per shipper, or show me the most recent order per customer, right? So it's not like the max or min, because we need to return not just that aggregate, but also additional elements from that most recent row. So let's say the row with the maximum order ID for the shipper, I'll need to actually show maybe also the order date, maybe also the customer ID, maybe other elements, right? So first of all, in terms of indexing, the type of index that tends to work best for top n per group tasks is it's not formally called like this, it's just a name I invented for myself, is an indexing pattern that I like to think of as a POC pattern. What does it mean exactly, POC? Well, think about the elements involved. We are after n most recent orders per group. The group element or the partition element is your P. Yeah, I call it P because to me it means partitioning. So think about, give me the most recent order per shipper. Your partition element is the shipper ID. Then the order element, it's quite obvious. When I say most recent, what do I mean? Do I mean the one with the more recent date, or do I mean the one with the highest order ID value, right? So let's say, just for simplicity, we'll say that to us, the one that is interesting is the one with the maximum order ID for that shipper. So the ordering element in our case will be order ID descending, okay? And then C stands for coverage, yeah, or covering, maybe you want to call it. This is the rest of the columns that you have in your query. If I need to return the order date and the customer ID in addition to the partition and ordering elements, then my covered elements are, in this case, order date and customer ID, right? So this is what I think of as POC. Now, the P and O elements, you want to determine order in the index. Namely, these need to make your key list. The covered elements, you just need them in the index, but you don't care about the order, so you put them in the include clause of the index, right? So remember POC, that's what makes it easy for me to remember what kind of index I need to create. By the way, a friend of mine, Adam Mechanic, I'm guessing many of you know him, said that he tried this acronym on an audience, and he said it was a bit hard for them to remember it. And also POC is used for so many other purposes, proof of concept and a bunch of others. So he said he tried to take the second letter in the coverage part, O, and he told them try to remember POCO, and it seemed to catch much better. So, whatever works best for you is good. So following these guidelines, if I want the most recent order per shipper, here's our POC index here in this case. So notice on the orders table that we create an index with the P part first, shipper ID, the O part second, order ID descending, and then in the include clause, we place all the rest of the elements that we want. Now, if we want to return the order with the maximum order ID per customer, then the P part is the customer ID, and of course the O part remains the same, and then the included parts are, again, the rest of the elements that you will need to incorporate in your query, right? So this is the POC index for the shipper's case, and this is the POC index for the customer's case. Right? So now let's have a look at the solutions. So if we are now handling the task for the low density case, namely for the customer, show me the order with the maximum order ID per customer. Well, we want to see a scan. What kind of strategy will give us a scan? Well, the easiest way that I found to do this is using a row number function. So here's how we do it. We go ahead, compute a row number. So let's say row number over partition by customer ID, order by order ID descending. Let's call it row num. Now we need to filter only the rows where the row number is less than or equal to our n in the top n per group. So when we want the one row with the maximum order ID, n is equal to 1. So we'll filter only the rows with the row number being 1. If we want the 3 rows with the highest order ID values, we'll need to filter the rows where the row number is less than or equal to 3. Now, a row number, as the case is with all window functions, is only allowed in the select and order by clauses of a query. So you cannot just say in the where clause, where, and then embed the row number function and that range that you want. Or you cannot refer to the alias of the expression within your where clause, because in logical processing terms, the select is evaluated after the where and not the other way around. So the kind of common trick is to define a table expression based on the query. And then we'll do the filtering in the outer part. We'll say select only what we need from C and then add the filter. Now, before I add the filter, I just want to show just the computation of the row number, what kind of plan we're getting, and then we'll add the filter on top. So what do we want to show? We want to show order ID. We want to show order date. We want to show shipper ID. And we want to show a customer ID, right? So before we apply the actual filter, look at the query plan. It's a plan, well, actually, because I didn't return the row number, you see the optimizer was smart. It optimized out the calculation of the row number. But let me just show it to you. This was kind of funny. So look at the query plan and observe, we get a scan. That's the only way that SQL Server knows how to deal with row number computations, even if we add a filter. So we scan the POC index in order, and then you see these two operators called segment and sequence project. These are responsible for the actual computation of the row number. And having a POC index in place, they cost almost nothing. Look at this. Look at the percentages of the cost here. Now, what exactly do they do? Think of segment as the element that is responsible for the partition by. Yeah? It simply emits a flag to the next operator, telling it whenever a new partition starts, or a new segment, that's how it calls it, starts. So think of a kind of a flag like 1 or 0. It's the first row in the segment, it will emit a 1. It's not the first row in the segment, it will emit a 0. And then the sequence project is a very simple task. If it sees it's the first row in the segment, it produces a 1. If not, it adds a 1. So nice and very efficient streaming calculation, provided that the POC index exists. If we didn't have a POC index, what would happen is you would see here an extra operator after an unordered scan of whatever is the nearest index that contains what we need, possibly just a clustered index. And then here you would see a sort operator being added. The data must be sorted by the partition element followed by the order element. Okay, but like I said, if you can afford creating the POC index to support your solution, fantastic. We avoid the extra cost of sorting. So this is the scan strategy. Now the filter, depending on what's n in your top n per group task, we have the final part where we say where n is less than or equal to that number. If we want the 3 rows with the highest order IDs, we say 3. If we want only 1 row with the highest order ID, we say 1. So the only thing that should be added now to the plan is here, we should be able to see a filter operator that takes care of the filtering part. And maybe I should use the correct name here. So our column name is not n, but rather row num. Okay, let's look at the query plan. And exactly what we expected, you can see the filter operator that actually is responsible for the filtering part. Now, if we want the same thing, but per shipper, we will get the exact same plan because the optimizer doesn't know how to do it differently. Even though theoretically, we could think about the optimizer having a bit smarter logic and saying, wait a minute, I see that you're filtering only the top row for each group, and I see that you have very dense group. Let me go and use this kind of 6 strategy, similar to what I kind of explained earlier with the simpler group kind of query, right? But again, the optimizer just doesn't know how to do this, so we will need to kind of nudge it in the right direction. How do we do this? Well, we already know. The cross-apply operator, given a POC index, will use the 6 strategy, right? So let's write a top n per group solution for shippers. So we'll say select from shippers. Let's call it in short S. Then there's the cross apply. Let's call the apply table expression O. Here we say select all of the columns. We're going to project, of course, just the ones we need in the outer query, so it's quite all right here to say star. And of course, don't forget the top in this case. So top, you know, whatever is your n. Remember, in our example, n is 1, so we'll say top 1 from orders as O, and then there will be the where O.shipper_ID equals S.shipper_ID, and then comes the ordering. So order by O.order_ID descending. And then in the outer part, basically the same elements that we returned previously, we will return here. This one comes from O, this one comes from O, this one comes from S, and this one comes from O. So let's have a look at the query plan. Finishes instantly, just like you can see. And this time, it's not just the order ID that we return per shipper, rather it's the entire row where the order ID is the maximum for the shipper. How come it finished so quickly? Well, we already know. Again, we see a scan of the tiny shippers table. We get 10 rows back, and then a seek per row that goes into the beginning of that shipper section in the index and then advances only one step with the top operator and returns all of the information that we ask for, as you can see in the output list. The order ID, customer ID, the order date, the last part, shipper ID, of course, we take from shippers, right? So this is how we get the SIX strategy. All right, so this concludes the 3 different examples. Now, it seems like we have 5 more minutes before the QA part, so I want to show a very kind of recent discovery that kind of turns this example over its head in a way. A very, very kind of interesting surprise as part of a private discussion that we had in kind of a private group. I'm guessing many of you know Erland Sommerskog, or at least know of him. Erland is a fellow MVP that focuses on all kinds of interesting T-SQL kind of topics as part of his work. He wrote a number of very nice papers on things like dynamic SQL, error handling, dynamic search conditions. I'm sure many of you know him. So he introduced a similar problem to the one that you see here, but with a catch. And then we had a discussion in that group between us with Erland and Paul White, I'm guessing many of you know, and we had Hugo Cornelis. We had a number of folks there in the discussion. And what Erland presented was this. He added one more column to the query. Let's say we want, in addition to what you see here, just one more column that is currently, and that's the catch, not part of our POC index. Okay, so let's say, for example, I wanted to return also the employee ID. Now, if I ask you, how do you think that the plan should change? Most people will say, what we are now expecting to see, since this index doesn't cover anymore, we expect this index to return just the element that will help us get to the related data row, and then we want to see kind of a nested loops operator here that simply performs a lookup that now will go to the clustered index that we have on order ID, and then we'll apply a key lookup to obtain the rest of the information. So this is how we expect the plan to look like, right? And then we expect to see, instead of, you know, the 10 6 that we currently have, we're supposed to see 10 plus a few more 6 for the applicable rows that we got back from the inner activity. Just a simple key lookup. So we still expect it to finish in almost no time and cost maybe, you know, instead of 40 reads, maybe 60 reads or so. But also finish instantly. But notice what happens in practice. I'm going to run the query, and it's running, and it's running, and it keeps on running, and clearly something very bizarre is going on here. It took 9 seconds to finish, and if we just kind of quickly check the statistics, what's going on here? It's you know, over 1 million reads that took place. We expected it to finish in maybe 60 reads. And then when we look at the plan, it's clearly not the plan that we anticipated. We do start with shippers. We do get 10 shippers back. But then instead of seeing a seek in the POC index and then a lookup in the clustered index, we see a scan of the clustered index per shipper. So what is the strange thing that is happening here? Well, for this, you need to understand the optimizer's kind of assumptions about what's the likelihood to get matches here. We have a clustered index that is defined currently on the order ID. But obviously, the clustered index leaf row is the entire data row. So naturally, it will have within it the shipper ID column. So the optimizer relies by default on a number of assumptions. One of them is called the containment assumption. So those of you who work a lot with cardinality estimations, you know of the 4 kind of basic assumptions. The containment assumption says that if we're looking for something, it exists. You know, so notice, well, maybe we'll look a bit more closely. Notice the predicate that is used as part of the scan of the clustered index. The predicate says where the order shipper ID is equal to the shipper ID that we got from the shippers table. So under the containment assumption, it says if we're looking for this shipper ID, it exists. Now let's think for a moment. we have 5 distinct shipper IDs in the table. So this means that the probability to get a match is 1 to 5. Now, if we touch 5 rows, we should already find statistically the first match. So the optimizer says, wait a minute, statistically, I'm expecting to get a match as soon as I touch the first page, very likely. Whereas using the other strategy that does first a seek in the POC index that is not POC anymore, it's missing the C, and then a lookup, this should cost me probably something like 8 reads, I'm going with this strategy. What this assumption fails to figure out or to realize is that if there are some shipper IDs that don't even exist in orders, for each of those, we're going to complete a full scan of the orders table with all of its 10 million rows. Now remember, we have 10 shippers, but only 5 of them have related orders in this particular orders table. So 5 times the plan completes an entire scan. Think about it, right? So some of the kind of fundamental assumptions that the optimizer makes for its cardinality estimations are simply not going for the kind of optimal scenario. They're just statistically okay, but if we have some shippers with the out-related orders, obviously the other strategy is kind of safer, you know. So there's no safety net here. It's just a very bad situation. How do we fix this? And again, I want to do this without any physical changes and without hints. Obviously, we could extend our index to include this column, and that's it. We're back to the original plan that we had. But suppose we're not allowed to make any structural changes. Well, the next option is to go ahead and specify an index hint. We could do this, and we would get the correct result. But again, the challenge that I want to introduce here is I want to do this with just query changes without hints, without performance hints. So when Erland presented this solution, what came up to me is this kind of pattern that I didn't have a name for it before because it was the first time I used it. But nowadays, I like to think of it as the proxy apply. What does it mean, the proxy apply? I will go ahead and use another layer of a cross apply that will deliver for the given order ID all columns to the outer layer. So notice how we do this. We say cross apply and then have another kind of layer. Let's call it O2, let's say. And then here we'll say select everything from the orders table, which we will name O2, where the O2 order ID is equal to the O order ID. And then look at what we're doing in the outer part. Instead of delivering the columns from O, what's not currently covered by the POC index, what we're doing is we're delivering it from O2. So as far as this query is concerned, this one, the index that we have is actually a covering index. And then because the inner query is a very basic inner order ID equals outer order ID, it's certainly going to give us the desired seek. So let's go ahead and run it and see that this is what happens. Boom, it's finished already. It didn't take the 8 or 9 seconds it took before. And here's this beautiful plan that we were trying to achieve, right? So as you can see, we start with shippers. It's perfect. Get 10 shippers. Now we do the seek in our original POC index. So this happens 10 times. And then you see how the loop simply goes and applies a key lookup in order to collect the rest of the information that we need. What's the total cost? Look at the number of reads. Remember, we had over 1 million previously. Look at the runtime. It's not 9 seconds. It's actually almost nothing, just 79 milliseconds, right? So in short, this is what I meant that we sometimes kind of need to nudge the optimizer in the right direction. I don't want to underestimate the optimizer's capabilities. So it's really an amazing software component, and thinking about what Microsoft managed to achieve with it is really quite, profound. But then again, it's not perfect, and we need to be able to kind of identify its weaknesses. We need to know what kind of logic simply doesn't exist within it, and then we need to be able to rewrite our code in a manner that we understand that will get the type of plan that we want. We want to minimize this kind of tuning and prefer, generally, obviously, the types of solutions where the optimizer has more flexibility and can do the job on its own. It just doesn't happen in all cases, right? So if you want more information, first of all, I remind you, you have the source code available there in the T-SQL SolidQ website. Also, we have a 5-day advanced T-SQL class that during 5 days covers information like what you just attended in this seminar. So I'll be very happy to see people in my class. We run it quite frequently. You can just go to solidq.com and look at the schedule there. All right, so we have, let's see, 5 minutes left. I'll be glad to take questions if there are any. And in the meanwhile, let me maybe deliver the presentation to Bill.